Okay, so let's try a couple of examples finding the flux of a two-dimensional vector field across a curve. So here's my curve C here, and I have a certain direction associated with it because I'm starting at -1, 1, and I'm going to 2, 4. And then you can see the vector fields in blue here. And I'd like to basically be able to quantify how much of this field is flowing across this curve. And by direction of cross, we need to all decide what we mean by across. And so we're defining this normal vector to point to the right as we're moving along the curve. So we're trying to see how much of the vector field is flowing in that direction as we move along the curve. So we've set this up last time. Let's just remind ourselves to actually do this line integral. We're going to change variables and rewrite everything in terms of a parameterization. And so we're going to need to rewrite our vector field in terms of t. And then recall n is going to be dy dt negative dx dt, then divided by that magnitude, which the magnitude in this case is just the speed, and then ds is the speed dt. So at the end of the day, I really don't need to worry about the speed anymore. I just need to find the blue vector up here, the f of r of t, and then this dy dt negative dx dt. So first step is going to be to parameterize the curve. And so the easiest way to parameterize y equals x squared is just to let we'll just let x be t and y be t squared. And in this case, we're going from -1 to 2. And then f of r of t is going to be given by t squared negative 2t, because up here you can see f is really y negative 2x, or yi negative 2xj. And then we need to find dy dt and negative dx dt. So using this piece here, let's notice that this means that dx dt dy dt, which is velocity, is just going to be 1, 2t, which means that dy dt negative dx dt, which you can see is going to be normal to that, is just going to be, it's going to be normal to the velocity, will just be 2t negative 1. So now I'm taking the dot product between these two vectors and integrating, which is going to give us the integral from -1 to 2 of 2t squared plus 2t dt. And when you do that out, we're going to end up with 21 halves. So the fact that this is a positive flux, and again, what we could interpret this as is, suppose that we interpreted this as a velocity vector field where it was measuring like the velocity, let's say, of water that's flowing through this region here in meters per second. Then this is telling us we would expect the amount of water that would pass through this curve measured in meters squared per second. So if we just looked after 1 second at the area of the water that had passed through this curve, we would get that it was 21 halves meters squared after 1 second. Okay, so now let's try another one. So I want you to go ahead and put this on pause. Find the outward flux of this vector field shown here in blue across this circle of radius 2, centered at the origin. Okay, so first we're going to parameterize the curve C. The easiest way to parameterize a circle of radius 2 is going to be 2 cosine t, 2 sine t, or some variation if you wanted. In this case, because I know that I would like it to be outward flux, I need to make sure that I at least parameterize it to be counterclockwise like this. So this is the simplest way to do that. And then let's just get the other pieces of info we're going to need, because this is dx dt, dy dt. So we'll just start out with this from the beginning. And then that's going to tell me that this component, the dy dt negative dx dt, which is the component that's pointing in the same direction as n, it's just not scaled. So it's not a unit vector yet, but it's pointing in the same direction as n, and that's just going to be 2 cosine t and then 2 sine t. And then next, let's evaluate our, change variables in our vector field and put everything in terms of our parameterization. So that's going to give me, this is normally 2x, but x is 2 cosine t, so this is going to give me 4 cosine t, and then negative 3y is going to give me a negative 6 sine t. And now I'm going to take the dot product between this and integrate. Okay, and then recall from Calc 2, one of the ways you can do this is we'll split it up, and then I will use the double angle formula because this is an even, because this is an even value for this trig function. So I'll use the double angle formula to convert this to an integral that I can do more easily. And then when you actually integrate and simplify, we're going to get, this is going to be 8 pi, and this is going to be minus 12 pi, which is giving us negative 4 pi. And again, what this means is if you're looking at this vector field, and if we were thinking of this vector field up here as being water that was flowing, for example, and we wanted to know how much of it was flowing out of this circle as opposed to in a given time period, we can now see that more of it's flowing in than out because our net outward flux is negative 4 pi meters squared per second if this was a velocity vector field. So we'd have more of it passing into the surface than coming out at this point, and this is quantifying the rate. All right, so now let's imagine what would happen if we wanted to find the flux not just through a curve anymore, but through a surface.